In this video, we briefly introduce the polarization selective bifunctional metasurface for high-efficiency millimeter-wave folded transmit array antenna with circular polarization. The relevant work can be found in IEEE transactions on antennas and propagation. Most of the conventional transmit array and reflect array antennas have large profiles, which are limited by their focal distances. To solve the problem, folded transmit array antenna is proposed based on ray tracing principle. However, the folded transmit array antenna requires two carefully designed functional metasurfaces, which will introduce additional loss and lead to a low aperture efficiency. We noted that the metallic surface can inherently reflect circularly polarized wave with simultaneous polarization conversion. Therefore, when combining a metasurface and a metallic surface, and integrating a circularly polarized antenna in the center of metallic surface, a low-profile folded transmit array with high aperture efficiency is achieved, which can be applied in the compact systems of 5G millimeter wave communication. We first design a polarization-selective bifunctional metasurface that works at millimeter wave frequency based on receiver-transmitter structure. The metasurface achieves copolarized specular reflection 4+Z RHCP incidence, and cross-polarized transmission with arbitrary wavefront manipulation 4+Z LHCP incidence. The receiver-transmitter meta-atom is actualized with three metallic layers, which is composed of an LHCP receiving antenna and an RHCP transmitting antenna with a back-to-back configuration. The bottom antenna can receive the LHCP wave, while reflect the RHCP wave, supporting the polarization selective characteristic. According to the unique property of circularly polarized wave, the phase response of transmitted wave can be modulated continuously by rotating the top transmitting antenna. Benefiting from the high-performance meta-atoms and total reflection from bottom metallic surface, the proposed folded transmit array antenna achieves a broad 3 dB gain bandwidth of 15.8%, a high aperture efficiency of 43.1%, and good polarization purity while keeping its low profile of 1.23 lambda at millimeter wave frequency. More details of the work can be found in the reference. Thank you for your attention.
This video is intended to introduce our research on interferomatic phase transmit array for spatial power combining to enhance ERP of millimeter wave transmitters. First, we will introduce the current state of research. Since the metasurface can adjust M waves, they are widely used in high gain and low loss antennas. But the conventional metasurface has limitations. They can only adjust the beam in a direction. Therefore, our goal is to design a metasurface that can adjust the multiple waves in different directions. Second, we will introduce the principle of interferomatic phase metasurface. According to the focusing phase distribution, calculate the phase distribution due to the difference in the propagation path of phase 1 and phase 2. Then superimpose the two parts of the phase. Interferomatic phase metasurface can focus two waves radiated by different phase to both sides of the metasurface. The two focused beam can achieve spatial power combining. The phase distribution and model are shown in Figure 5. Using a patch antenna as the phase source, if the two phases are excited separately, the radiation through the metasurface forms beam perpendicular to the metasurface. If two phases are excited at the same time, the two beams are superimposed into a higher gain beam. This is the process of spatial power combining. This is the measurement setup. A transmit array and two phases were fabricated. They are assembled using a 3D printing fixture. The transmitter has focused two M waves from different directions to both sides of the transmitter array. This feature has realized the spatial power combining with low loss and capacity. Furthermore, the method can be extended to more ports and other frequency bands. Please feel free to contact us if you have any questions.
In this video, we briefly introduce a wideband high-efficiency transmit reflect array antenna for bidirectional radiations with distinct circular polarizations based on a metasurface. The relevant work can be found in IEEE Transactions on Antennas and Propagation. The transmit reflect array antennas combine the merits of transmit array and reflect array antennas, thus the beam coverage is successfully extended from half space to full space. The general development of transmit reflect array antennas undergoes an evolution from conjugated beams to independent beams. However, it is still a challenge to exploit a transmit reflect array antenna with independent beamforming and distinct circular polarizations. We proposed a strategy to design a transmit reflect array antenna with distinct circular polarizations based on a polarization-dependent full-space metasurface. It is clear that the metasurface can let the LCP divergent wave pass through and form an LCP high-gain beam in the far-field region, while the incident RCP divergent wave is reflected as a tilted RCP high-gain beam. The transmission phase and reflection phase are modulated independently so that the bidirectional beams can be designed with arbitrary directions. Different from the Pankaratanambari phase that only exists in cross-polarized transmission, here we proposed a method to continuously modulate the copolarized transmission phase, thus the polarization diversity is achieved. The accordingly designed metaatom is composed of two LCP microstrip patches with a back-to-back configuration. The intrinsic chirality of the LCP microstrip patch can naturally receive the LCP incidence but reflect the RCP incidence by rotating the top and bottom patches separately. The reflection phase and transmission phase can be modulated independently. According to simulation results, the reflection phase is determined by the angle beta, while the transmission phase is controlled by angles alpha and beta simultaneously. Therefore, once the required transmission phase and reflection phase are determined, the rotation angles of the top and bottom patches can be calculated accordingly. We fabricated a polarization-dependent full-space metasurface, and assembled the final transmit reflect array antenna by employing a Fermi antenna as the feed source. The aperture is optimized as a rectangular shape for a higher aperture efficiency. The transmit reflect array antenna achieves bidirectional radiations with good merits of independent beams, broad bandwidth, high aperture efficiency, and high polarization purity. More details of the work can be found in the reference. Thank you for your attention.